This is section 2.6, related rates. So related rates are an application of derivatives that helps us find how things are changing in relation to each other as time goes on. So when we're solving related rates problems, our first thing we want to do is to draw a picture. Once we've drawn a picture, we want to write an equation relating the variables. So if it has to do with volume, you would write your volume equation, area, write your area equation. Sometimes it might be the Pythagorean theorem or the distance formula. So you're just going to find an equation that you can write for the situation. Then we're going to find the derivative of that equation with respect to t. And then we're going to write down what we know and what we don't know, and then plug in what you know to find what you don't know. So a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So first thing I want to do is I want to draw a picture. So when we drop a pebble in a pond, we get a circle. Okay, and then the circle just gets bigger in all directions as it goes. And we have a radius. And for our equation, well, we're talking about area. So I'm going to write the area of a circle. So A equals pi r squared. Take the derivative with respect to t. So it's like that implicit differentiation. So it's dA dt equals 2 pi r dr dt. And now let's see what we know. So our variables are dA dt, r, and dr dt. We're trying to find how the area is changing. We know the radius is 4 feet, and we know that it is increasing at a rate of 1 foot per second. So we're going to plug in what we know to solve for what we don't know. So dA dt equals 2 pi times 4 times 1. So we get dA dt equals, dA dt equals 8 pi, which is about 25.13. And we're talking about area per time, so feet squared per second. All right, let's look at another example. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So we're talking about a spherical balloon. So I'm going to do my best to draw a sphere. So three-dimensional, here's my radius. And we're talking about volume of a sphere. So I'm going to write my equation, V equals 4/3 pi r cubed. And I'm going to take the derivative with respect to time. So dV dt equals 4 pi r squared dr dt. All right, I'm going to list my variables. And I'm going to plug in what I know and what I don't know. So dV dt is how the volume is changing. Well, air is going in, so it's increasing at 4.5 cubic feet per minute. Our radius is 2 feet, and we're trying to figure out how the radius is changing, so dr dt is our unknown. So we have 4.5 equals 4 pi times 2 squared dr dt. So 4.5 equals 16 pi dr dt. And when we divide, we get about we get 0.0895, and the radius is measured in feet, time is measured in minutes, so that is our rate that we're looking for. All right, last example. A light is mounted on a wall 5 meters above ground. A 2 meter tall person is initially 10 meters from a wall and is moving toward the wall at a rate of 0.5 meters per second. After 4 seconds of moving, what is the rate of the length of the shadow changing? So let's draw our picture. So I have my wall, and I have a little light up here, and then I have a person standing. Here's the ground, and the light hits the person and creates a shadow. We know that the wall, or the the distance from the ground to the light is 5 meters, okay? And that's not gonna change, so we can use that right away. Same thing with the height of the person. The person's height isn't gonna change. I'm gonna let the distance between the wall and the person, I'm gonna call that A, and I'm gonna call the shadow length B. So what I see here is I see two similar triangles. There's one, and here's the other one. So they're similar triangles. So remember, similar triangles, we can write a proportion. So in this case, our equation 2/5 is going to equal B over A plus B, and I can cross multiply to get 2A plus 2B equals 5B, and then I'm going to subtract the B's over, so I get 2A equals 3B. So this is my equation. Now I want to take the derivative, so I get 2 and then dA dt equals 3 dB dt. So we need to know, so dA dt and dB dt are our variables. Well, we know that the person is walking toward the wall at a rate of 0.5 meters per second, so dA dt is negative 0.5, because it's negative because it's getting smaller, and we're trying to find dB dt. So plug in, whoops. And then when we solve, -1 equals 3 dB dt, and we get that dB dt is going to equal -1/3, and we're talking meters per second.